Hello, my name is Pedro. I'm a professor here at Cleveland State, and today I want to talk to you about a recent publication we have at the journal Transportation Research Record. The problem we're facing here is dealing with predicting traffic density. Traffic density or traffic occupancy deal with congestion. So how many cars do I see on the road? How much of the road is being occupied by cars at any given time? And look at the word probabilistic here. So we're dealing with the problem of not predicting exactly how many cars we're going to see, but the probability of distribution of how many cars we're going to see. So we're going to see less than 3 cars with this probability, less than 30 cars with this probability, less than 300 cars with this probability. So having the full distribution for that. This is a very interesting problem because traditionally, historically, as you can see here, we have just using ordinary traffic data, doing some pre-processing, some basic forecasting model, and then I do a point estimate prediction. So this is most models do nowadays. And this is very useful for the decision of route planning or real-time navigation. However, there are many sort of decisions that require a more nuanced prediction, a probability distribution. Smart city traffic changing, dynamic toll pricing, mitigation situations. So when I'm going to create some mitigation practices for congestion, should I base this on a certain guess of how many cars I'm going to see, or should I base this on probabilities, right? So usually probabilities are more appropriate for that type of problem. The situation here is that a lot of probabilities, they deal with extreme rare scenarios that we don't see very often. So for example, an accident might cause really extreme congestion, or a snowstorm might cause an extreme congestion. Those are not the common things that we see every day. How do we incorporate those non-recurrent events into our model? Just to give you 2 examples here is that we had 2 non-recurrent events here that we tracked: a Bears game in Chicago and a snow day, a snowstorm in Milwaukee. As you can see here, the green lines, they represent a typical day, a typical occupancy here, or a percentage of the road that's being occupied by car. As you can see in the Chicago area here, around the game, around the stadium, the green line is very constant, a little lower during the early hours of the day as expected, and tapering down at night when people go home. However, as you can see with the dots here, the Bears game caused a lot more cars to show up in preparation for the game right before the game, creating that peak there. How could I have predicted that? So if I'm just using ordinary traffic data, it's very easy for me to miss that type of change. Similarly, a snow day in Milwaukee, as you can see here on the green line, it's usually much higher than what we actually saw. Meaning, in that particular snow day, we had much fewer people going to work or going to the grocery store, more people staying at home. How can we incorporate that type of non-recurrent data into our model and create this probabilistic? The way we incorporate this is using a machine learning model called MQRNN, Multi-Quantile Recurrent Neural Network. And we were able to show that they apply very well for this type of problem. And there were some technical problems with the baseline model that we also tackled. The result was very astounding, as you can see here in the results. So we have the same situations here, the Bear game and the snow day in Milwaukee, and 2 different models, 2 benchmark models, so common models people use nowadays, and then how it compares to our approach. So looking at the Bear game here, GBM are gradient boosted machines that are very common algorithm for prediction that people use. As you can see here, it does a good job sort of predicting the peak here, predicting the peak, but you can see the model is very uncertain. As you can see, the bands for the probabilities here, they're very wide, meaning the model is not super certain. For example, here the model could say, oh, my guess is that I'm going to see between 10 and 100 cars with 90% probability. It's a very wide margin that's not super helpful. So even though the model is correct, maybe I saw 15, 20, 30 cars, it's not super useful. As you can see on the plot A here, our model, it's much tighter. So our model is saying, I believe I'm going to be seeing between 20 and 23 cars. So a much tighter range, much more useful for decision making. Very similarly, we can see here on the snow day, we have another model called RMAX that's also a benchmark commonly used by time series forecasting. And we can see a very similar thing that's happening here. RMAX is doing even worse than GBM at predicting the changes there, and it's being even more uncertain. The bends are very, very wide. Compared to our model, much tighter margins, meaning that now when I'm doing time series forecasting for congestion, when I'm predicting how much congestion I should be seeing, I can be much more certain, much more confident on the bends, and I'll have a much more tight margin to work with that I can be more sure um, of the number of cars that I'm likely to see with the probabilities. This is very useful for mitigation practices. So a government or can decide with much more certainty where to target their efforts for mitigating congestion when and where they need it. And that's it for this paper, and I appreciate you watching this. Thank you so much.